Chapter 3.1 is about the nodal analysis. The goal of the nodal analysis is to find the voltage on each node in the circuit. Let's take a look. So in the nodal analysis, the variables in the circuit are selected to be the node voltages. The node voltages are defined with respect to a common point in the circuit. Typically, we call it a ground. So the voltage of the ground is 0, and we have the node voltage, that is the voltage with respect to the ground. And once all node voltages are known, we can easily obtain the current flowing through each element. So here, let's take a look. For example, we have two nodes, that is the node M and the node N. When the voltage at node M and the voltage at node N is known, we can easily calculate the current flowing through the resistor, which equals Vn minus Vn over R. So this is Ohm's law. So no matter how complicated our circuit is, once we know the voltage of all the nodes, we can easily calculate the current on each element. So our goal in nodal analysis is to calculate the node voltage. In this example, we have node 5 selected as the reference node, that is the ground, and we have the node from 1 to node 4. In this example, the node voltage are given. For example, the node voltage at node 1 is 12 volts, and the voltage at node 2 is 3 volts. The voltage at node 3 is 3 over 2 volts, and the voltage at node 4 is 3 over 8 volt. By given these node voltages, we can easily calculate the current on each element. For example, I1, it's obvious that I1 equals Vs minus Va over 9K. This is Ohm's law. And how about I2? I2 is Va minus 0 over 6K. And I3 equals Va minus Vb over 3K. So using similar method, we can obtain I4, I5, and So this example tells us that it is very important to obtain the node voltage, and once the node voltage is obtained, we can easily calculate the current on each element. So the steps to determine the node voltage. So in our circuit, in this example, the node voltage is given, but most of the time that the node voltage is not given, we need to calculate the node voltage by ourselves. So there are 3 steps. First, we select a node as a reference node and assign voltages to the remaining n-1 nodes. And second step, that is apply KCL to each of the n-1 non-reference nodes. Use Ohm's law to express the branch currents in terms of the load voltages. And finally, solve the resulting equations to obtain the unknown node voltage. Let's take a look at an example. So this example is from our textbook. So we have the node 3 as a reference node, and we have node 1 and node 2. So we need to write 2 KCL equations because we have except the non except the reference node, we have two other nodes. So for node 1, let's write KCL on node 1. We can see there are two resistors connected with node 1, and there's a current source connected with the node 1. So let's write the KCL. That is I1 plus I2 equals IA. So that is the current leaving node 1 equals the current entering the node 1. So we can write G1 using Ohm's law. G1 is I1 equals G1 times V1. How about I2? I2 equals G2 times V1 minus V2, and it equals IA. So we can simplify this equation, that is G1 plus G2 times V1 minus G2 times V2 equals IA. So this is from the KCL on node 1. Similarly, we can write the KCL on node 2. That is, it has one current source connected with it and two resistors. So let's write the KCL at node 2, which equals that the current entering I2 equals the current leaving equals IB plus I3. So we have so we have I2 minus I3 equals IB. For I2 is equals G2 times V1 minus V2. For I3 is equals G3 times V2 equals IB. So we simplify this so we can obtain that G2 V1 minus G2 plus G3 times V2 equals IB. So we can obtain these two equations. And in these two equations, we have two unknowns, that is V1 and V2. Two unknowns, two equations. We can solve for the value of V1 and V2. And here we can write these equations in the matrix form and plug in the numbers. So we have the G matrix and V matrix and I matrix, so that V equals the inverse of G times I. So we can use MATLAB to calculate the node voltage. So in the previous example, we followed the 3 steps of nodal analysis. The first step is to select the reference node, and the second step is to write KCL on each non-reference node, and the third step is to solve the equations. And in some scenarios, we can write the equations in the matrix form directly. That is, if the circuit with independent current sources, so that this circuit only has independent current sources. It does not have independent voltage sources. It does not have dependent sources. So this only applies to the circuit with independent current sources. We can write the node voltage equations in this matrix form. So in this matrix, the diagonal element is the sum of conductance connected to node K. And the off-diagonal elements, we can see that they are symmetrical. GKJ equals GJK. So which means G12 equals G21. G1N equals GN1. So they are symmetrical. And they are the negative of the sum of the conductance directly connecting nodes K and J. And here K is not equal to J. And V is the vector of unknown voltages. And I is the current. It is the sum of all independent current sources directly connected to node A, with currents entering the node treated as positive. So if there is no independent current sources connected with that node, we just set it to 0. So let's take a look at this very simple example. So in this example, we have node 1 and node 2. Let's write this in matrix form. So for node 1, the R1 and R2 is connected to node 1. So the conductance is 1 over R1 and 1 over R2. So the element G11, it equals the sum of the conductance connected to node 1. So which means that it equals R1, 1 over R1 plus 1 over R2. How about G12? Between the node 1 and the node 2, there's R2. And be careful, that is the negative of the sum of the conductance. So this is negative R1 over R2. And G12 equals G21. So here is symmetrical. So this is also the negative 1 over R2. How about G22? Let's take a look at node 2. The R2 and R3 is connected to the second node. So it equals R1 over R2 plus 1 over R3. So this is our G matrices. And the I matrix, it has 2 elements because we have 2 nodes. For the first node, we have IA connected to the first node, and it is entering the node, so it is positive. So that is IA. For the second node, we have the independent current source IB, and it is leaving the node, so we have negative IB. So we have G, we have I. We can calculate the voltage, which equals the inverse of G times I. So we can obtain the value of the voltage of each node. Let's take a look at another example. So for this example, we have one more node. In previous example, we have 3 nodes, and we select one as reference node. So we write the KCL, or the matrix is a 2 by 2 matrix. So here we have 4 nodes, and we select 1 as the reference node, so we need to write KCL for the 3 nodes. And also we can write in matrix form directly by observation. So let's take a look. So for node 1, we have R1, R2, and R3 connected to node 1, so that G11 equals 1 over R1 plus 1 over R2 plus 1 over R3. And how about G12, that is between the node 1 and node 2, there's R2, and remember the negative sign. And between node 1 and node 3, there's resistor R3, so that is the negative R3. And according to the symmetry, we can determine the element G21. And how about G22? G22, we have R2, R5, and R4 connected with node 2, so we can obtain the G22. And G23, there's R5 between node 2 and node 3, so that is 1 over R5. And also according to the symmetry, so G31 equals G13, so and G32 equals G23, and G33. For node 3, we know that 2 resistors R3 and R5 connected with node 3. So we get the G matrices. How about the I matrix? For node 1, we have the independent current source IA entering the node 1, so that is IA. For node 2, it does not have independent current source directly connected with node 2, so it equals 0. And for node 3, we have an independent current source, but the current is leaving the node, so it is a negative IB. So we have G and we have I. We can calculate the V by taking the inverse of G times I. So this is the nodal analysis by observation. So we didn't write the KCL for each node, but we observe the circuit and write it in the matrix form. Let's take a look at one more example. So here we have, for example, this is node 1, node 2, and node 3. For node 1, we can see that the R1 and R2 is connected to node 1, so that is R1 plus R2. And between node 1 and node 2, there is no resistor between node 1 and node 2, we write it 0. And between node 1 and node 3, there's R1, so that is negative 1 over R1. And according to the symmetry, G21 equals G12, which is equal to 0. And for node 2, the R3 and R4 is connected to node 2, so that is R1 over R3 plus 1 over R4. And between node 2 and node 3, we have R4, that is the negative 1 over R4. And we can, the G31 equals G13, negative 1 over R1. And G32 equals G23. And G33, which take a look at the node 3. Node 3, R1, R4, and R5 is connected to node 3, so that is R1, 1 over R1 plus 1 over R4 plus 1 over R5. So we get the G matrices. And the I matrices. For node 1, we have the current IA leaving node 1, so that is the negative IA. For node 2, the IA is entering node 2, so it is positive IA. And also there's IB leaving the node 2, so that is IA minus IB. And for node 3, there's no current source directly connected with node 3, so it equals 0. So we obtain this equation, and by plugging the numbers and use MATLAB, you can calculate that the voltage equals the inverse of G times I. So we introduced how to write the equation in the matrix form by observation, but this only applies to the circuit that only consists of independent current sources. What if the circuit contains dependent current sources? And also the previous matrix is symmetrical, and if the circuit contains the dependent current sources, the circuit is no longer, the matrix is no longer symmetrical, and it cannot be modeled by inspection. We need to write the KCL on each node. So the method that write KCL on each node applies to all the circuits. Okay, let's take a look. For node 1, let's write the KCL. That is the beta times I1 plus 1 over R1 plus V1 minus V2 over R2 equals 0. And for node 2, we have V2 minus V1 over R2 plus I0 minus IA equals 0. And we know I0 equals V2 over R3. So we can simplify these two equations, and we can get G1 plus G2 times V1 minus G2 minus beta G3 times V2 equals 0, and the negative G2 V1 plus G2 plus G3 times V2 equals IA. Let's write these two equations in the matrix form, which equals G1 plus G2 negative G2 minus beta G3 minus G2 plus G3. This is G. And how about I? The first node is 0 and IA. So we can write it in the matrix form. And by plugging the numbers, we can solve for the voltage. The other example also contains the controlled current source. So we need to apply KCL at each of the non-reference node. For example, the first equation, let's write the KCL for node 1. So that is G3 times V1 plus G1. This is minus IA equals 0. And for the second node, that is IA plus G1 V2. And for the third node, And also we have the Vx equals V2 minus V3. So by plugging Vx into the equation, we can obtain the equation in the matrix form. So that is the G1 plus G3 times V1 minus G1 times V equals IA. So the circuit is no longer, the matrix is no longer symmetrical, so we cannot write it in matrix form by inspection if there is a controlled current source. But now we have 3 equations and 3 unknowns. We can solve these equations to get the value for V1, V2, and V3. We can still use MATLAB to solve V1, V2, and V3. But the difference is that the matrix is no longer symmetrical. Another scenario is that the circuit contains independent voltage sources. In the simplest case, that the circuit only controls that independent current source. That is the first scenario. The second scenario is that the first scenario we can write it in matrix form by inspection. The second scenario is that the circuit contains dependent current source. So we apply KCL on each node and write the equation. This is the third scenario, that is a circuit containing independent sources. And the independent voltage sources, the simplest case is that the independent voltage source, one terminal is directly connected with the reference node, that is the ground. For example, here, the 12 volts, it is connected to the ground. So it's obvious that we know the voltage on V1, that is 12 volts, and the voltage on V3, that is the negative 6 volt. So when the independent voltage source is connected to the reference node, it simplifies our analysis, because our goal is to find the voltage on each node, and here we can easily obtain the voltage on node 1 and node 3, but we do not know the voltage on node 2, so we still need to calculate the voltage on node 2, but we can apply KCL at node 2. So here that is V2 minus V1 over 12k plus V2 minus 0 over 2k plus V2 minus V3 over 12k equals 0. And we know V1 and V2. So the only unknown variable in the equation is V2. So we can solve for V2. So then we finish the nodal analysis. We obtained the voltage on all nodes except the reference node. The other case is that the voltage source is not directly connected with the ground, that is with the reference node. So in this scenario, we need to form a supernode by enhancing dependent or independent voltage sources connected between two non-reference nodes and any elements connected in parallel with it. So here let's use this, let's plot this circle, and this is a supernode, and we apply KCL at the supernode. This gives one equation. The other equation is the relationship between the voltages of the two nodes enclosed in the supernode. So here that is the v1 minus v2 equals 6. So let's take a look at this example. So for this supernode, we assume that the current flowing through resistor, the 6K resistor is I1, and the current flowing through the 12K resistor is I2. So we can write KCL on the supernode. So that is we assume the current entering is negative. So that is the current entering plus the current leaving the node. Equals 0. And we have also v1 minus v2 equals 6. So two equations, two unknowns, we can solve for the value of v1 and v2. So this is how we solve this problem. Let's take a look at another example. So this example has three independent voltage sources. Two of them are directly connected with the ground, and one is not directly connected with the ground. So we choose a supernode. And the voltage, we have two nodes in the supernode, V1 and V3, and their relationship is that V1 equals V3 plus 12. So V1 is 12 volts higher than V3. So let's apply KCL as the supernode. So here the V1 equals V3 plus 12. So we have V. So here the V2 equals negative 6 volt. V4 equals 12 volts. It's obvious because they are directly connected with the reference node. So let's write the KCL at the supernode. So we have V1 minus negative 6 volt over 2K plus V3 V1 minus 12 over 2K and plus V3 minus 1K plus V3 minus 12 over 1K plus V3 over 2K equals 0. So we can solve for the V3 because we already know that V1 equals V3 times 12. We plug in, so we can calculate V3, and then we know, once we know V3, we can calculate V1, and V2 and V4 is already known, so we solved. Then we finished the nodal analysis on this circuit. So another more complicated case is that the circuit containing dependent voltage sources. But the method is similar, so we use the supernode. So we use this supernode. So we have V1 over minus V3 over 6K plus V1 over 12K plus V2 over 6K plus V2 minus V3 over 12K equals 0. And we have V1 minus V2 equals 2 times Vx, and V3 3 is 6 volt. So once we obtain this equation, we can calculate V1, V2, and V3. So let's have a summary on the nodal analysis. And first, determine the number of nodes in the